start the final session of today. The speaker is Gabor Csany from the University of Cambridge. We'll talk about advances in interatomic potential for materials.
Thank you. Okay, thanks very much. So of course, first, like many others, I have to start by congratulating CECAM on its birthday. I cut my teeth in CECAM in Lyon in 2003 and have many good friends and colleagues from there. Looking at this lineup of speakers, I feel like these little bears who climb up to the trees to appear a bit taller. So here's the outline. I'm going to tell you about the use of machine learning to advance the state of interatomic potentials and simulations. So first, I'll tell you a little bit about my thoughts about multi-scale modeling and molecular dynamics, and then a few thoughts on fitting functions in high-dimensional spaces, descriptors, regression, regularization, and then I'll spend about the last third of the talk telling you about a few applications, just so you get the feel for what are the current capabilities. So there are, of course, we all know that there are multiple scales of materials modeling, and actually the CECAM members, lecturers, visitors, and speakers span quite a large size in this range. But if you look at the different methods, at the very low end, we have quantum chemistry and quantum Monte Carlo, and they are the only ones which are truly considering the Schrödinger equation in all its depth and beauty. And of course, I put very provocative scales at the horizontally for capability and vertically for accuracy, but essentially you can't do time scales with those methods. And then the most prominent method in terms of citations and publications is density functional theory, and it somehow hits a sweet spot in terms of applicability and capability. You can simulate hundreds of atoms for picoseconds. And there are, of course, various simplifications of density functional theory going generally under the moniker of empirical quantum mechanics, which allowed you to extend some of those length and time scales at the expense of lowering the accuracy. And then the method that leaves electrons behind and considers only atoms, and that's what the rest of the talk is going to be about, are interatomic potentials. Okay, so there's a big gap here. The gap is also because we've left the electrons behind. So if you look at the bottom scale, then we have a gap of 1,000, factor of 1,000 in the number of atoms that we treat, or in the time scale. So it's a gap, but also there's a gap in accuracy, not just in capability, but also in accuracy. So while for the methods that where electrons are involved, I sort of indicated some attempt at some accuracy quantitatively. What are the typical errors per atom that you have for structures of interest? But for interatomic potentials, generally the accuracy is qualitative. Sometimes you might get decent accuracy, sometimes it's completely off the scale, and that's because we've coarse-grained away the electrons. But if we want to do molecular dynamics, that is really about moving the atoms. So really there ought to be a way of doing dynamics of atoms, but as we heard at the very first talk in this celebratory conference, that makes sense. Forces on atoms make sense in the context of the many-body wave function. So the whole research program that I'm interested in for about the last 10 years, and of course building on, and I'll show you some of that, building on earlier work, is trying to get this sort of capability because we've left the electrons behind, but with this sort of accuracy. First principles molecular dynamics, and we're going to have to stop treating the electrons explicitly. But we shouldn't really need them. We're not interested in the electronic structure. We're not interested in the wave functions. We're only interested in the forces on the atoms. So if you look at who spends what on HPC time, then it turns out that in the US, much more time is spent doing molecular dynamics with interatomic potentials. So this is the 2017 report of Blue Waters, one of the largest supercomputers in the USA, available for non-military use. And this is ordered by codes, and this is a log scale in terms of node hours, and all the red bars correspond to simulations of interatomic potentials. The ones on the left are, as you won't be surprised, they are biological simulations, and this one is LAMPS, which is mostly material simulations. And then there's a jump in scale, so this is the expansion of that bar, and the green bars correspond to first principles, typically DFT simulations. And then so the LAMPS bar actually is larger than all the first principles simulations combined. Interestingly, in the UK, this is reversed. And of course, the absolute scale is contracted by a very large factor also. But here in the UK National Supercomputer, and this is slightly older data, but the first principles simulations are use about twice as much computer time, 2 or 3 times as much as interatomic potentials. That simply reflects the interests of the community and the history of development in those two academic communities. So there are 3 large areas where interatomic potentials are developed and used. And the first one are organic force fields, and really they are known for their transferability. So I list here on the right-hand side some of the names that you will be familiar with, but these potentials are very accurate for very small displacements. So they are parameterized for small molecules and then used for large molecules, and for small displacements around equilibrium, they are very good. Typically, they don't do reactions, with a few exceptions, and the ultimate fit of all the parameters is made to macroscopic experimental properties. So heats of solvation, vibrational frequencies, and so on. And the parametrizations is also rather simple. So you would have a pair potential, V2, some potential on the angle between 3 atoms, that's V3, and maybe a dihedral angle, V4, that involves 4 atoms. But notice that typically all of these parametrizations involve a single variable. So even the angle potential is just a function of the angle, even though it involves 3 atoms. It's actually just a very simple function of its angle. The dihedral involves 4 atoms, but 6 dimensions, but it's really only a function of the dihedral angle. And if you go to slightly larger displacement, slightly heat the system up, like we did for this decane here, there's no quantitative accuracy. So here's AI Rebo, which is a potential widely used for simulating hydrocarbons, and this is the predicted energy of this decane as a function of against DFT B-lip, which is not too bad for these hydrocarbons. And you can see that, of course, it captures a basic chemistry, right? But there are errors on the order of half an eV. So another field where interatomic potentials are used are solid-state materials physics, material science. And these potentials need to be reactive because the interests of this community is about bond formation, bond breaking, melting, formation and migration of defects. And again, typical names here, which many of you will recognize. And here's the typical functional form. It's the functional form of EAM. So you take an electron density rho around each atom, and on an atom you add up all the neighboring electron densities, and that gives you a scalar, and then a simple one-dimensional, one-parameter function is applied to that. It's the embedding function. So these models are physics-based. So these functional forms, the rho and the v, are derived from physics, and in fact can be derived from density functional theory, but it's not systematic. So if these simple functional forms don't do what you want, there's nothing you can do to systematically improve it. And that's not what typically people want to do. They use the simplest model to capture the phenomena. Some feature of V, some feature of rho, maybe add a dash of an angle term or something, and that captures some essential feature of the system that they study, and that's in some sense in the best traditions of physics, but it's not first principles modeling. The fitting of these potentials is usually a mixture of fitting to experimental data and to some extent ab initio data. And the accuracies are really not very good. So this is an example for, quantitatively, this is an example for silicon. And look at all the colored bars up here. These are sort of leading potentials of different types for silicon, and this is percentage error versus DFT, and the different bars represent different simple properties. So this is elastic constant, surface energies, vacancy, and interstitial formation energies. And you can trade them off one against the other, so every now and then you find errors that are very small, but then for other properties the same method would give you a very large error. And depending on which DFT you parameterize to, one error goes down, the other error goes up. There's a third area, which is gas phase molecules. So for very small molecules, there's been a very long tradition in quantum chemistry to systematically fit the Born-Oppenheimer potential energy surface. So these are polynomial basis sets. Whoops. These are polynomial basis sets usually applied onto a systematic expansion of all the coordinates. So what I indicate here is a little tetrahedron, but you would start with a pair, a triplet, a tetrahedron, and then a 5-simplex and a 6-simplex and so on, symmetrize all their coordinates. That's a non-trivial task, and then fit to quantum chemistry data. So the scaling of these procedures is exponential in molecular size. So in around 2000, people could do it for 5 particles, 5 atoms, and nowadays they can do it for 7 or 8. And the potential evaluation of the potentials gets very, very expensive. So what we'd really like to do is unite all these 3 fields. So unite them because there are systems of interest which have molecules and solids, and we want to compute them very accurately. For example, vibrational spectra, which the quantum chemists need their very accurate models for. But also, we would like to have, so we need all these systems in the same framework. But I would also like to unite these leading properties. So I would like to have potentials that are disaccurate, reactive, and transferable, like the organic force fields. So the first question we should ask is it possible to create an accurate reactive interatomic potential for covalently bound materials? And it would be nice if we could answer this question without trying very hard to make one. Like before we make one, we should try and ask whether quantum mechanics actually allows this. So the true quantum mechanics is a many-body theory, and it has long-range interactions. So there's charge transfer, polarizable electrostatics, van der Waals dispersion. And it's going to be very important to separate long and short-range interactions. We don't really have a hope of doing many-body physics in the long range. And so the first question is whether we can separate the many-body part and the long-range part. So there are 3 possibilities to deal with the long-range interactions in sort of order of increasing sophistication. And the first one is to just don't do it, right? And you can do that if they're small enough to be ignored. So for example, if you investigate materials with the same type of atom, then there is no charge transfer and there's no electrostatics. That you're left with van der Waals, which is weaker, smaller, and shorter range. Or you can say that actually I know the analytical form of electrostatics and maybe even van der Waals dispersion, and we can make analytical models and subtract that from the data and fit the rest using our many-body method that is systematic and nice and reactive and so on. Or, and this is the third most sophisticated method, we can try and fit parameters of these long-range analytical interactions, and very few people have attempted that. That's sort of still in the future. So the question is, once you've done one of these 3 things, you've dealt with long-range interactions, how local is the remainder? So what we define as short-range, and of course quantum mechanics doesn't have an intrinsic separation, but once I've used one of these methods to deal with something that I call long range, when I subtract it, I call the remaining part short range, and the question is, how short is it? So we can actually have a theory about that. We can measure that. So we all know about weak locality in quantum mechanics. So that's the sparse representation of the electronic ground state. So this is a little sketch of a tight binding scheme. So if you have a Hamiltonian, they have one-body wave functions and eigenvalues, then you can construct this projection operator, which is the density matrix, and the forces will be the trace of this density matrix times the derivative of the Hamiltonian. And this density matrix in insulators and for metals at sort of elevated temperatures will be exponentially localized, right? So its elements will be less than exponential some gamma, which depends on the gap or temperature times the distance between the atoms on which those orbitals lie. But that's not enough to make an interatomic potential. What you actually want is what I would call strong locality. And that means that the forces and higher derivatives are independent, on an atom, are independent of the far field. And this is mathematically different. One can take this relationship and show that this strong locality holds. And that means that once this strong locality holds for the forces, then one can prove that there exists a compact atomic energy function, and otherwise known as an interatomic potential. So some epsilon energy function that's a function of just the neighboring atoms, that's the compact part, and so the total energy can be written as a sum over atomic energies. And it's sort of like a convolution over atoms. And you will have heard convolutional neural networks for machine learning, but this is the same idea, because we know that there is symmetry, translational symmetry in materials. So this, by doing convolution over atoms, we already achieved that. And so mathematical work of this type has started recently. So my friends Chen and Ortner in 2015 have proved this mathematically, that you can make this transformation. This was very limited to a screen tight binding model with a fixed Fermi level, but perhaps extensions to DFT and beyond are possible. We can, of course, investigate this question numerically. So here's an example of how we would do that. So let's take a system. The illustration here is just a graphene sheet. That's easy to draw in 2 dimensions. But imagine any covalently bound material, and I pick an atom here at the center, this red one, and I draw a sphere around it and fix every atom inside that. I take a sample from somewhere and I fix all the atoms. And then I replicate the system, make many copies of it, and move the atoms outside the sphere independently in each replica. And I measure the force at the center in each of those replicas. That's F, and I measure the variance of that force. And that tells you something about the locality if you look at that variance as a function of the radius of this sphere. Because basically the question you're asking is, how much does the force on an atom depend on whatever is outside a given cutoff radius? So here are some measurements using DFT. So in diamond, if you take the fixed sphere radius to about 5 angstroms, the forces, the variance of the force is basically gone. It's 10 to the minus 2, so it's 0.01 eV per angstrom. Of course, for graphite, it decays much, much, much slower because the gap is extremely small here. If you take amorphous carbon, so I have one at 2 grams per cubic centimeter, I have one at 3 grams per cubic centimeter. Amorphous carbon at 2 has many more sp2 bonds. Amorphous carbon at 3 has many more sp3 bonds. And here are the same curve with random distortions of the atoms, and here are where the replicas are made with molecular dynamics. And you can see that broadly the trends are the same, and amorphous carbon at 3 grams, more similar to diamond, decays very fast, but even amorphous carbon at 2 grams per cubic centimeter does decay, although much slower. But it does depend on where you take the configuration. So if you just make random displacements, then you will change the electronic structure much more dramatically, and there's very, very weak decay in the amorphous carbon at 2 grams per cubic centimeter. But what this tells us is that it gives us a limit on force field accuracy in principle, like without having to think about how we fit it. So for a given cutoff, this curve tells us what is the achievable accuracy in principle. And we can take a look at the materials that we're interested in and ask, is it actually ready? Are we ready to create an interatomic potential? So the new approach, the systematic approach, the hope that we're going to achieve this goal was basically kick-started about 10 years ago, first in this paper by Jörg Behler and Michele Parnello, and a couple of years later by us. And what we were promising everybody is that using modern high-dimensional fitting techniques, we're going to create DFT-accurate force fields. So what I'm here to tell you is what happened, right? What happened in the last 10 years. So how are these potentials made? So basically, this is a one slide on regression. So how do we fit high-dimensional functions? So linear regression is the favorite of all mathematicians. So imagine that X is a vector in some high-dimensional space. Eventually, it's going to be the atomic positions transformed in some way. And F is, for example, the atomic energy function that we're going to fit. And if we have some basis functions, B, then we can define F as a linear combination of these B functions. And of course, the quality of this and the accuracy and the efficiency will depend on how good these B functions are. So then it's very hard. What should the basis functions be? Nobody knows. So then kernel regression, the method that I typically use, says, I don't know what the B functions, I don't know what the basis functions are. So, but I can make a linear fit using a trick. So the trick is to define a kernel function, k, which is a function of two of the points in configuration space, and it plays the role of a similarity function. If x equals xi, or x equals x prime in general, then k is 1, and the least similar x and x prime are, k just goes smoothly to 0. And if I have a function like that, which is much easier to create than basis functions, then I can use them as basis functions. And this is called the kernel trick. It's a very, very general idea. So that you don't need to invent a fixed basis set, you can, as long as you have a similarity measure. And then you can make a linear fit. Now, in this linear fit, what is xi? It's a database. So you create a database, that's where you've measured some data, and your basis functions are essentially your similarity kernel with one of the arguments sitting at the database points and the other argument being the free variable. There are some few interesting facts about this fitting method. It's equivalent to a neural network, which has one hidden layer, which is partly why you never see anybody using a one hidden layer neural network. It's also equivalent to something called a Gaussian process. I won't mention too much about that, but there are essentially two communities that have done the same thing for a few decades, and then they came together recently. And here's sort of a picture idea. So here's X is where I want to ask what the function is. I have some database, and some of those database points I choose to carry around, and essentially I have to measure the similarity of my new point to all the other points in my database, and they form the basis. And then there's nonlinear regression, which is neural networks, basically. And if you have more than one hidden layer, and interestingly, almost all the neural networks that are being used for interatomic potentials for materials have two hidden layers, right? So not one, because that would be the same as kernel regression, but those practitioners have not really found the need to go beyond that. So here's what a two-layer neural network looks like. So it's essentially a function like this. So h is some nonlinear function, typically a sigmoid, so it looks like this, and then this is the functional form. So it's recursive. So you have h outside, and then there's a constant b, then there's a sum, there's a set of weights, there's another h, and inside that another b, another sum, and so on. And this is the pictorial representation that you usually see. So these w's are weights, the b's I didn't draw, they are biases, and this two hidden layer neural network corresponds to this function, where all the b's and the w's are just numbers. They're numbers to fit. And in all of these methods, the red indication is what you need to state before you do the fit. So for linear regression, you need basis functions. For kernel regression, you need a kernel function and decide what your database is, where you're going to have your representative configurations. And for neural networks, you just need to decide about this h function and also the number of units that you're going to have. And after that, you take your data and you optimize. There's another trend amongst these three methods. That's the reason I had them in this order. Because I'm going to, in the next slide, talk about what X should be. So what is the space in which we do this optimization? And it's not hard to understand or get a feel for the fact that with linear regression, it's all in the B. If your B is wrong or not appropriate, it's going to be a terrible idea. And with kernel regression, there are some universal Ks. So a Gaussian K is sort of a universal approximator, but your N might need to be quite large. And certainly your XIs, your database that you carry around, needs to be appropriate. And if your K is not appropriate, then it might take a very, very large N for this to converge. And for neural networks, they're also universal approximators, with H being the sigmoid, and N and N1 and N2 being sort of moderate. So you need to take much, much less care about what your input space is. Neural networks are extremely flexible, and so you don't need to be so clever about what your input space is for neural networks. So how do we represent systematically in a many-body way the neighborhood of an atom, and then therefore which we can plug into one of these regression methods? So suppose that you have this atom whose energy I want to fit, and it has a bunch of neighbors, maybe 4, maybe 20, and I want a description of its many-body neighborhood in a continuous systematic way, but also one that obeys symmetry. So if I permute two atoms that have the same nucleus, I don't want the energy function to change. If I rotate this entire system in the lab frame, I don't want the energy to change. So the Weil matrix, this matrix of distances on the diagonal and dot products, so angles on the off diagonal, is the canonical set of invariants which completely characterizes the neighborhood. But it's really a very bad idea to deal with these invariants, because this matrix is not permutation invariant. So, right? So if I list two of the neighbors in different order, then the appropriate rows and columns of this matrix is going to permute. So if I have a function of this matrix, it's not going to be automatically invariant. By constructing the matrix, I have fixed the number of neighbors. I can't solve these problems by dropping the atom ordering. So here's an example which, if you've seen it, it's sort of trivial. If you haven't, it might be surprising. So these are two tetrahedra which have 6 sides which are exactly the same length. But the two tetrahedra are different. Right? You can construct such pairs of tetrahedra that have exactly the same side. So just the fact that you know all the distances between points doesn't mean you can reconstruct the positions of those points. You also need to know which are connected to which triangles are connected, which distances form triangles. So a completely different way of constructing invariants is to think about the atomic neighbor density function. So in this case, I'm going to consider this atomic energy as a function of the neighbor density, which is constructed as follows. It's centered on the atom whose energy I'm interested in, and I put a delta function on each of the neighbors, maybe with a finite cutoff that is a parameter of the whole scheme, and that rho is the neighbor density. It just add up all those functions, and perhaps I can smear the atoms a little bit later. It turns out that that's a good idea, and that just means putting a Gaussian on each atom, a narrow Gaussian, so you can still distinguish the atoms. And this is great because this rho is translationally invariant. It's always centered on the given atom that I'm interested in. It's permutationally invariant with respect to permutations of the neighbors. It's also continuous. So I can remove an atom from the neighborhood. If I take one of these atoms out of the neighborhood and I have a smooth cutoff function, then this rho neighbor density changes smoothly. But it's not rotationally invariant. Right? If I rotate the laboratory frame, then all these points, all these delta functions or Gaussians are going to rotate. So this rho itself is not rotationally invariant. So I need rotational invariance of rho. And it turns out that one can do that. So we can project this rho onto rotationally invariant basis sets. So this is a piece of understanding that came much later than 2007 or 2010. But it turns out that the Weyler-Parnello symmetry functions, as they called them, the way they described the atomic neighborhood, is a projection of this neighbor density onto certain rotational invariant basis functions. The bispectrum that we used in 2010, and I'll show you the formula a little bit later, is also a projection, a different projection of this neighbor density, and many, many others. So the wavelets, Stefan Malat's scattering transforms, and histograms of lengths and angles that are favored by friends Anatol von Lilienfeld and Matthias Rupp are also essentially projections of this same neighbor density. So the trick with the symmetries is the same. So my favorite projection is the smooth overlap of atomic positions, and the name comes from the way we discovered it. We went about it a completely different way. We didn't want to construct descriptors, we wanted to construct a kernel. So the way we thought we want to construct a kernel is that we take this density, this atomic neighbor density, and we take two of them, rho and rho prime, because that's what we need for the kernel method, right? Some sort of similarity metric, and we construct the overlap integral of them. And that's not yet rotational invariant, but I can make it so by integrating it over all 3D rotations. So we take this S, we square it, we integrate it over all 3D rotations, and then we get this 6-dimensional integral, and that is now rotationally, permutationally invariant, continuous and smooth. It turned out that it's really hard to evaluate though, right? It's a 6-dimensional integral for every single atom in my system. It turns out that if we expand this neighbor density in spherical harmonics using some radial basis G YLM for spherical harmonics, I have expansion coefficients CNLM, then after lots and lots of algebra, it turns out that this 6-dimensional integral is exactly equal to P dot P, where P is C dagger C, where C is a vector of these coefficients, the M index, the magnetic quantum number. The M index is the vector index. So this, because this kernel is just a dot product, this Pi is a complete set of invariants for describing this rho. We call it the SOAP vector or the power spectrum. It's also sort of reminiscent of Steinhardt's bond order parameters, QL, if you take the radial basis to be the identity. So Gn just is 1. Of course, we don't really, because we want radial information. So Gn is a complete orthonormal basis. But that's the rotational part is the same as Steinhardt's order parameters from the early 90s. So if you take this kernel and you exponentiate it, you take it to the second or third power, that's what we're going to use as our kernel. So that's the similarity kernel. We're going to carry around our database and use this kernel to make to approximate the function. And it is a universal approximator, and that's because it's based on a complete set of invariants for the neighbor density. I like it because it has very few free parameters. So the three that are here on this slide are this atom sigma, so the smearing of the atoms, the cutoff, and that cutoff has to be part of any interatomic potential, and this exponent, which essentially is 2. So very, very few parameters. The sigma is basically 1 Bohr, because it's the size of each atom. We don't really change it. So essentially, there are very few parameters. They're all set from physical considerations, and the kernel then is defined and is always the same. There have been an explosion of research since 2010 with many, many extensions, and I would highlight 2 of them. So Michele Ceriotti is here at EPFL, a good friend and colleague, and we became interested in this way of defining functions, and has extended it in many, many different directions. So he's fitted many, many molecular properties using this kernel, including, for example, NMR chemical shifts. He's also extended this scheme for learning not scalars like the energy, but tensor properties. So it turns out that if you do that same 6-dimensional integral, but you insert this Wigner matrix of order lambda, so lambda equals 0 for a scalar, lambda equals 1 for a vector, 2 for a second rank tensor, and so on. So if you do this integral, and the same trick with the spherical harmonics works, so you never actually need to perform the integral itself, you can just create a lambda power spectrum, then you can learn tensorial properties that transform covariantly in the proper way. And for example, he's used this to fit the electron density. So take take a molecule like this, and you compute the electron density from DFT in many different configurations, and then you take the electron density, you decompose it into a bunch of different spherical harmonics itself, and you learn the coefficients, and they transform using different orders, different lambdas, and you use this kernel to make a kernel fit to them, and you get an extremely accurate representation of the electron density. So you need, here's some data for small hydrocarbons, number of training molecules. Just a few dozen training molecules is enough to get the electron density basically with 1% error. So that's this is from last year, and I think it's going to lead to great things. There's a much more recent paper by Ralph Draughts from Bohm, and he made this theoretical connection between all the different neighbor density-based descriptors that I mentioned. So all of my and other people's work in the past 10 years, Ralph put it on sort of a same footing, and he further generalized the invariance. So he basically said that the pair potential, the SOAP vector, and what we originally used in 2010, the bispectrum, they're all part of one series. So the C dagger C is what I called the SOAP vector before. Ralph calls it a B2 because it has two C's. And the bispectrum, which I didn't mention, has, oh, sorry about that, it has three C's, and he calls it a B3. And this complicated thing is a Wigner 3J symbol, but it's just a constant for different L's and M's, and it's also invariant. And he says, look, you can do this for 4 C's and 5 and 6. And this forms a very, very natural extension of all these invariants. And maybe if you use all of them, you can make much more accurate fits. You can make basically linear fits rather than kernel and neural network fits. And that has many, many advantages for speed and perhaps also for accuracy. So there are many, many competing schemes. Here's a little table, and I think that the next few years is the times of a shakedown. Essentially, who's going to be more accurate for the same data, who's going to be better at extrapolating. Computational cost is a big consideration. So here's some sort of summary in terms of properties of some of these different schemes. So they're all based on the density. SOAP, so my groups using SOAP, we smooth them with the Gaussians. The other groups do not. They use delta functions. The basis set for SOAP is complete because we use this complete set of invariants, the second order spherical harmonics. SNAP is based on the bispectrum. Ralph Draughts' basis functions again are complete. Baylor-Parnello neural networks have a manual way of selecting the different symmetry functions. Moment tensor potentials are created by Alex Shapiev, and again, there's a manual selection. The dimensionality of these different fits is different, so we have high dimensions. Baylor-Parnello symmetry functions have high dimensions. SNAP, MTP and Draughts have much lower dimensionality. Different people use different regularization schemes, and the regressors are different, each to his own taste, right? So there's lots and lots of different competition. Here's some performance using some of these methods. Ralph's is not in here yet because it's just too new. But you can see there's a bunch of elemental metals. So nickel, copper, lithium, molybdenum, silicon, and germanium. So some few semiconductors thrown in. And here's the basic accuracy over the entire data set. Darker is better. Here's as a function. Here are the learning curves as the number of training structures, and you can see significant differences. Each set of training sets is exactly the same. Here are the error distributions in predicted molecular dynamics runs. So there are significant differences between these methods. GAP and MTP come out very well out of this, right? So here are these GAP and MTP here. They have GAP. I think it has a complete basis set, and MTP is very, very carefully tuned basis sets. There's, of course, the cost versus performance. And here you see GAP is the most expensive. SOAP, anything to do with spherical harmonics gets very, very expensive. MTP is the cheapest and certainly has the best performance cost ratio. But MTP has a polynomial basis. So if you can take density-based descriptors, but if you don't use these nice, smooth kernels that we developed, but use the simple polynomial of the of your neighbor density, then you might run into the following trouble. So here's some data on silver palladium. We fitted it on just FCC configurations, different configurations of where silver and palladium atoms are. And here's a test on liquid data. And the test, this is gap versus MTP, and the tests come out pretty similar. So these is energies, and the median error is about 10 millieVs. The median force error here is about 10 to the minus 1, which is very, very good, 0.1 eV per angstrom. The phonon spectra, this is against DFT. They come out very, very well for both methods. So all is well, and MTP is 100 times faster. So what's the problem? What about doing an actual molecular dynamics of a large system in the solid state? So here is a transition pathway between two of these different FCC configurations. So here's an FCC configuration, here's another one, and we just linearly move the atoms between one or the other. This is the DFT path. There is a large barrier for making FCC from FCC. Here's the gap path. And of course, remember, the training is only done at the endpoints, right? Only at FCC. And gap gets it wrong by a factor of 2. But here's MTP. And this is a log scale on energy. So MTP gets it wrong by a factor of 50 minus. Okay, so there's a dramatic drop here, and this is a trap for this potential, and you would fall into it minus 1,000 dVs at the middle of that transition path. So complete nonsense. And that's because of the polynomial basis. Polynomials are very, very poor at extrapolation. So now I'm going to show you in the remaining sort of 10 minutes a few, no? I have 50-minute talk. I have a 40 minutes, but fine. I'll show you some very small highlights of what's happening. This is a code that is available and is free for non-commercial use. And maybe this is the best slide to show you. So there are some successful applications to hard materials in 2018. So most of these was done with Volker Deringer. So what the point to take away from this is that there are a very large number of different materials. The method that's been used is exactly the same, so don't need to fine-tune anything for different systems. And you just crank these out. Different applications, not method development, but actually doing material science. Let me show you what the sort of things we can do. So clicking through some benchmarks, screw dislocations under stress for iron. So we fitted an iron model using sort of data from and graduate student in Nicola Marzari's group, Daniel Dragoni, and then we made a 50,000 atom model. This was done by Francesco Moresca and Will Curtin's group, and here's the stress-dependent Piles barrier for moving this dislocation in this very large system. So this is, we claim it's DFT accurate. You cannot do this any other way. Here's some amorphous carbon. Again, I'm going to skip to the highlight of the simulation, which is make an amorphous carbon potential. It describes amorphous carbon very well with respect to DFT, qualitatively better than anything else. And then you can do something like a deposition simulation. So here are 10,000 atoms of carbon deposited one at a time, and we grow an amorphous carbon film and study its growth mechanics. So previously people thought that the incident ion densifies and creates, due to its high impact, creates this high density region. That's not the case. So in fact, what's happening is peening. So the incoming atom actually lowers the density where it is and densifies in some sort of annular region around it. And the only way to do this is to have a DFT accurate interatomic potential. So then the last example is the silicon. So what we wanted to know is, can we actually make a model that encompasses everything that we want to know about this material? So the silicon challenge. And again, I won't show you the benchmarks, but a very, very wide range of silicon structures are in the database. And this previous slide where I showed you how bad the interatomic potentials are, generally, the bottom row is the SOAP gap model, right? So it finally gets every single property within a few %. There are properties that are not anywhere near the database. So this is a grain boundary. This is one of these It's a sigma-3 grain battery, and these are stacking faults. And again, those are within 10%. Delicate surface reconstructions, the famous 7x7 reconstruction here on the 111 surface, and here are all the other interatomic potentials. Here's gap against DFT, here's a zoom. So we put in the 3x3 into the database, and this delicate chemical balance between strain and chemical energy is reproduced really within the DFT error. Okay, so I won't bore you with the rest of the benchmarking, but let me jump to the conclusions, which is where we think these kind of simulations will go. Too many slides. 100,000 atoms of amorphous silicon perspective. So we have a baseline empirical model, electrostatics, strong repulsion, exchange repulsion, and so on. We don't yet have electrostatics, but we have the short-range bonding and the many-body dispersion. There was a talk earlier today by Max Waite, and he showed that. So the thing that's missing is systematic treatment of many-body electrostatics. And here are sort of the wish list, really. So we are reaching the limitations of DFT. For many systems, we have the capability of fitting something with milli-EV accuracy, and we need data sources that are very, very accurate. We need to combine with long-range electrostatics. Stefan Gödecker has done something in 2015, but people haven't really followed up. We need to combine the exploration and the fitting. The databases are getting unwieldy, so active learning, and there's some work on that. Minimal databases. What do we need for a given property? We can make much more widely applicable potentials if we can minimize the database sizes. Do we want higher accuracy? SOAP is very hard to beat for materials, but I'm sure it will be. And we could include magnetism, electronic entropy, and so on. And my overarching concern is to eliminate the fragility. So this extrapolation problem that I was talking about, I think that's going to be the most interesting. So thanks very much. I'm happy to answer questions.
Okay, we have time for a quick. Okay.
Can you hear me? Oh, thank you. I would like to ask the following. Maybe I missed it, but how do you encode within the network, the neural network structure, the symmetries, and the knowledge that you have, pre-knowledge you have on the physics of your problem? In our case, we did similar effort for the turbulence modeling, and we found that, in fact, injecting pre-knowledge was key to get good results.
I absolutely agree. So those are the descriptors. So these invariants that I talk about. Oh, I think Microsoft wants itself updated. There we go. So some missing slides. It's the descriptors that are. Oh, there we are. Let me show you that slide that you're talking about. Maybe if I go back to it exactly. Okay, so this is an example of a descriptor, this SOAP vector, the C dagger C. C's are the spherical harmonic expansion coefficients of your neighbor density. And this P is a complete set of symmetry invariants for the structure. Okay, and as long as you make, and there are many others, right, of similar kind. You take the neighbor density, you project it onto a set of basis functions, and that's the input. And you take that input and plug it into a neural network, you will have all the symmetries. I take this and construct a kernel using it. It's the linear dot product kernel. And therefore, the system is exactly invariant to all physical symmetries. And I agree with you that this is not being able to solve this problem is why this didn't happen before 2007. So nobody knew how to encode the symmetries in general for an arbitrary number of neighbors.
what about the dispersion? Because you have this short-range dispersion, but it's known that even for Lennard-Jones, if you cut too short, then you don't have a compressibility, for example.
Sure. So right. So long range is tricky, and I think one just has to be very level-headed about it. So the way we've solved dispersion is that we take some dispersion, including DFT, either MBD or D3 or VDV, I mean whatever VDV functional, and then one example that my former student Max Wade showed yesterday was with MBD, PB0 plus MBD, and you basically take a Lennard-Jones that fit to the same data, you subtract it, the rest is moderate range, and then you fit that using this kind of kernel with a cutoff that's about 8 angstroms. And you have controlled accuracy. You don't need, it turned out that wasn't difficult. And we could go to 10, not more. So I think, but if that wasn't, if the pair potential wasn't good enough for that was a methane system, then you have to do something else. But I think this idea of assuming that the long range is a lower body than the short range is the key to that.
All very beautiful. One question, is there a time when you stop learning? That is, no matter what the computational cost, if you put more and more data, more and more DFT data, does the maximum error go to 0, or at a certain point it stops, or do you have a sense of what's happening?
Yes, very much. So it depends, I mean, for a simple material, it really depends on the cutoff, right? So this idea that I sort of had here really is, we see it. So this limit, so you take the locality limit, and we can reach it, and therefore it becomes the absolute limit, right? So for example, take iron or tungsten, where if you take a 6 angstrom radius, then you can get to about 0.1 EV per angstrom error on the force, and nothing you can do can lower that other than increasing the cutoff, no matter how much DFT data you put in. But if you increase the cutoff, then you will need a lot more data because it's a much larger space, and I don't think that process can't go on forever. I think if you doubled the cutoff, the data requirements would be enormous, and the spherical harmonics kind of stop making sense. You have an atom that's 20 angstroms away, and you're trying to describe it reference back to the center with a spherical harmonics that makes 60 oscillations around you. That's sort of nonsensical. So I think going out to about 5 angstroms is reasonable. And so this kind of separation that I'm talking about is really driven by that. I want to create long-range models that take it down the locality to about 5 angstroms, because that's what I can fit with a reasonable number of basis functions, needing a reasonable amount of DFT data, 1,000 small cell calculations.
Okay, we have time for 2 more questions.
So just on this point, you could also include explicit electrostatics at long range, like multipolar expansions that evaluate the...
Sure, yeah, people do.
So why not in your case?
No, absolutely. I mean, no, people do. And I just wasn't, I knew that other people do that. I'm interested, there's only 24 hours in a day. So I'm interested in other aspects of the problem. If you have a good electrostatic model, and by good, I don't mean, you see, the problem is if you go to an off-the-shelf published force field that has electrostatics, it's been fitted together with everything else to give you some property that the authors wanted. But as the requirements here are different, I want an electrostatic model which gives me the best locality, so that if I do the locality test that I have on this slide, not on the original DFT forces, but DFT minus your model, fixed long-range polarized electrostatic model, I get the smallest locality as possible. That's actually hard, because people usually don't fit their electrostatics with this in mind. They fit it together with other stuff, right? So I'm not saying it's in theory a problem. It's just in practice, this is work. this is a lot of detailed work. But people do it.
Okay, our last question.
Yeah, that's an absolutely beautiful talk. What happens if you have multiple species, for example, carbon, hydrogen, nitrogen, oxygen?
I would have been able to show even fewer slides if I had. So all of these generalizes to multiple species very, very naturally.
But if you have them simultaneously?
Yeah.
How well do they behave, for example, if you have 2 or 3 or 4?
Yeah, that's what I mean. So basically the descriptors, the SOAP generalizes. You just gain a species indices, right? So you have a hydrogen channel, hydrogen density, a carbon density, an oxygen density, and you form the C dagger C between all of them. So that suggests quadratic scaling, right? So the length of your description is going to square quadratically with the number of species, which is not a problem for 2 or 3. People have done organic force fields with this kind of method. Michele Ceriotti has done organic force field with 6 different species, and it's a very natural extension of this scheme.
Okay, let's thank our speaker and all the speakers of today, and let's close the session.